So here's example 3. A projectile, like someone is throwing a stone up in the air with a speed of 50 meters per second. So this is like a physics question. I don't know if any of you are taking physics. Its height in meters is modeled by the following equation. So they give us an equation, and any equation that involves gravity, throwing anything into the air and letting gravity pull it back down, will always form a quadratic equation. So we get a t squared in this equation. We want to graph this function. So if we were graphing this without a graphing calculator or without graphing technology, you would have to plug in values for t and graph them. Now, I think we can solve t is time. I'm going to put that down here. H is height. I'm going to put that here. I think there's one mental math one that we can figure out right away. It's pretty easy, even though there's decimals in this question, that you could plug in 0. And if you plug in 0, I'm going to mark it right here, you get the point 0, 10. If the height is in meters, that means that when the object was thrown at time 0, it's already 10 meters above the ground. That's what that point means. When I plug in 0, the time is 0. That's the initial place. It's getting thrown up in the air. So what we have is this idea, and it will always make a parabola. Now, to find the other pieces of information on this parabola, well, we could plug in more values. Like you could plug in 1. If you plugged in 1, you would have 60 minus 4.9, so you would have approximately 1, oh, this is obviously very badly not to scale, 55.1. Can you see that that would be where that went? Now, if from here to here is 0 to 10, here to here 1, another 45, I have to wait. I have to do a little bit of cheating. That seems more realistic with the scale. Sometimes that happens. You start a graph, and you go, oh my goodness, the scale that I chose is terrible. I have to redo it. Now, if you have, well, everybody has a phone or access to technology. Some of you have graphing calculators. So if I go to the internet and I go to Desmos, I can type this equation in. So I go y equals negative 4.9 x squared. And to get to the little squared button, above the 6 is the little hat button that pushes it up as an exponent. Negative 4.9 squared plus 50x plus 10. Oops. Plus 10. And we notice that nothing happened because I wrote the equal sign again. Plus 10. We notice that we might have to scroll out here a little bit to get an idea of what this looks like. But we get our parabola. And what's nice about that parabola is you can click on it in different places, but it was really easy to click on the top point there and find out that the maximum is around 137.55. Okay, and so this is where, in a question like this, let's go back to our notes. What is it asking? Graph it. We now know that we have this point. Oh, I forgot the values. That point was at 5.10, 5.1, 137.55. Go back. 5.1, 137.55. So Desmos is wonderful for finding out answers easy and intuitively. Okay? Our graphing calculator can also find this out, so I'm going to pull that up and show Those of you that have a graphing calculator, how you use it. Maybe, there it is. So we have negative 4.9 x squared plus 50x plus 10. And on Desmos, I could scroll to zoom out. On your graphing calculator, if you want to zoom out, you have a couple of options. Okay? There is a zoom button. So hitting that zoom button is sometimes nice. Sometimes people like to zoom out, number 3. Sometimes, if you go down, at the bottom they have, whoa, wait for it, a zoom fit. Wow. Hopefully I can hit the right, there, zoom fit, I can push enter. It tries a little bit better to make it fit. I still don't like how this one fits. So on your calculator, there is a window button. And on the window button, I'm going to cheat a little bit because I saw the answer from Desmos. I know that my vertex is at 5. So for my maximum along my x-axis, I'm going to go a little bit more than double 5. I'm going to go to 12. And I know it went up to 137.5, so I'm going to go up to 150 for my y max. And now I get the shape of the parabola. Sometimes with your window on your graphing calculator, it's a lot of trial and error. You try something, don't like the window, try something else until you get a window that matches up. On your graphing calculator, you can find the maximum as well. It's not as intuitive as Desmos, because Desmos, all you did was like, ooh, click where the maximum was and it showed up. Really nice. On the graphing calculator, all of the calculations you can do with the graph are above your trace button. So above trace it says calculate, so you hit second and then calculate, and then it allows you to calculate your zeros if you want, maximums or minimums. In this case, we want to find a maximum, and what it asks is, well, what's something on the left side? So I go to the left side of my maximum by clicking, and I push enter, and it draws a little, some calculators just do the arrow, mine draws an arrow and a line. And then it asks you to go to the right side of your maximum. And I can either do this by clicking the arrowhead over until I get there, or if I can tell, like, ooh, it sure looks like 7 is going to be on the right side of the maximum, I can just push 7, push enter, and it'll draw the second arrow and second line at 7. Can you see that the maximum is in between those two arrows? So when it says guess, you go, I think it's going to be there, and push enter, and then it tells you exactly that it's at 5.10 and 137.55, the same that Desmos did. Okay? So, when was Desmos created? Not too long ago. When was the graphing calculator created? It's like already 15 years old. So you can see how newer technology on the internet is probably a little bit better and easier to use. Okay, so we find it. Now explain the significance of the intercepts, the coordinates of the vertex, the domain, and the range. So when we talked about the y-intercept, which we figured out to be 0, 10, in this situation, that's our starting height. When we talk about an x-intercept, and again, I'm going to go to Desmos because I'm going to say that it's probably pretty easy just to click on that one to find 10.4, 0. We can talk about its significance. What does the x-intercept, which we found out to be 10.4, 0, what does it mean? Do you think you could throw a ball up in the air with a speed of 50 meters per second? Okay? If you think you could, and this equation is actually, like, sometimes math textbooks like give you an equation and it has no real life application whatsoever. I can tell you that this equation is pretty much perfect. If you throw a ball up in the air and it takes 10.4 seconds to land, you will have thrown that ball up in the air at 50 meters per second. If it lands sooner, you obviously threw it up with less. If it takes longer to land, right, then you threw it up even faster. Right? You could shoot a rocket up in the air, and then hopefully it lands close to where you shot it up in the air and you didn't aim it in the wrong way, but you could time it and you could actually figure out how fast you threw it up as a result. Okay, so that's our x-intercept. So we've explained what the y-intercept and the x-intercept mean. Did you know that there's also an x-intercept over here? That makes no sense whatsoever. Because in this real life problem, time would only start at 0. There's nothing in the past, because that object hasn't been thrown up in the air yet. Our vertex. Our vertex happened to be 5.1, comma, 137.55. Okay? This part tells us the maximum. That's the max height that that object goes. It goes up 137.5 meters in the air. So the other thing you could ask yourself, if there was a building 137.5 meters tall, could you throw a ball on top of it? Right? Take a baseball. Go to one of those buildings downtown that has lots of glass windows. Try to throw it on top of the building. No, don't do that. That's a bad idea. But if you did, and you're like, oh, I broke the window on that floor, you can find out how fast you actually threw it up in the air using our quadratic equation. Okay? These are, I think it's okay to imagine doing that, but not actually going out and doing it. Right? Because I'm sure that the building manager, or when the police get involved, they said, what were you doing? And you said, I was trying to learn math. They would not be very impressed. Okay? And this part is the time when it reaches the maximum. So if you threw a ball up with 50 meters per second initial velocity, in 5 seconds it will reach that maximum height.
Yeah, they smell like hot glue cardboard.
The domain and the range. Now, this is an interesting question because quadratic equations, domain, is usually everything. Because an x squared equation can be everything. And any question you've had up till now that says, what's the domain of this parabola? You would write x belongs to the real numbers, that x, e, r, and you'd be fine. But when you get into a real life question, all of a sudden the domain changes. In this case, the domain only makes sense from 0 to 10.4. Because 0 is when the object was thrown. Negative numbers don't actually make sense. and 10.4 is when it hits the ground. Because if we went any further, look what would happen. This problem would keep going. So that would mean you threw your ball up in the air, and instead of hitting the ground, it just kept going straight into the ground and making a hole following through the whole time. That doesn't make sense. It would probably bounce. So in this question, this is the only part of the domain that makes sense. Because after it hits the ground, this is probably what would happen. It would bounce a little bit. The range also normally would be, the range would normally just be less than the maximum. So normally you would just write y is less than 137.55. This time it only makes sense from 0 to 137.5. Perfect. The questions for this one is just number 10.